Hi, this is a talk for the 2021 Computational Complexity Conference. I present a paper with Nati-Lineal, an improved protocol for the exactly n problem. The problem is as follows. There are three players. They receive three integers, x, y, and z, and they want or need to decide whether the sum of these integers is equal to n, some fixed number n. No, it's not a computational complexity problem. It's a communication complexity problem. You want to determine how many bits of information are required to determine this. And the rules are each player is allowed to look at two of the inputs in each time. And the players take turns writing messages on a public blackboard. So everything written or shared by a player is seen by the other players, and they see everything written so far, and they can base the current decision on that. There is not much known about this problem. The first result is already from the paper defining the model from 1983, a paper of Chandra, First, and Lipton. They defined this model, used it to prove lower bounds on some complexity problem. And this is in a way the first problem that they considered. They proved two results about the problem. First, they showed that there exists a protocol for exactly n that uses at most 2 square log n bits plus a negligible term. This is quite a surprising result, I think, for anyone seeing it for the first time. The size of the input is log n, and there is no obvious reason why there should be a non-trivial protocol at all. This is really surprising. And they also showed, using results from Ramrith's theory, that the complexity is not a constant. And now it's possible to maybe prove their results using Semiradi regularity lemma and other results. But even with the new methods, the lower bound is not even log star. So there's a huge gap here between the protocol, the upper bound, and the lower bound. And it makes sense that maybe you can improve the upper bound, but until this paper, no improvement was found. And one reason for that maybe is that their proof was a proof of existence, not a protocol. So it's not exactly clear what's going on. It was a reduction in a way to another problem, and not a communication complexity protocol, just a proof of existence. And in 2017, in a joint work with Nati-Lineal and Tony Pitassi, we wanted to find an explicit protocol to really understand what bits are communicated, what information you need to reveal about the numbers in order to determine that their sum is equal to n or not equal to n. And indeed, we did find such an explicit protocol with exactly the same complexity as Chandra, First, and Lipton. Not surprisingly, because we found this protocol by examining their proof. But understanding what's exactly going on did shed some new light on the problem, and we were able now to improve it a little bit. So this is the result in this paper, giving an explicit protocol different than the one from 2017. That is slightly better. Instead of a constant 2 square 2, you get a constant 2 square logged e times the square root log n plus this negligible term. Let me tell you some of the details for Chandra first and Lipton's proof of existence, then the more recent explicit protocol, and our improved protocol from this paper. For Chandra first and Lipton's proof of existence, first they used a lemma showing that a protocol exists if the following combinatorial structure exists. You want to construct a large set of triples, 3 numbers, without a star. 3 triples of the following structure: x, y, x plus y, x plus delta y, x plus y plus delta, and x, y plus delta, and x plus y plus delta. You can see that x appears here and here, and y appears here and here, and x plus y plus delta appears here and here. And if you draw these 3 triples in a 3-dimensional grid, it looks like a star or a corner in a way. And they show that if such a set exists, of course, such a set easily exists, but you need a large set, then you have a complexity, a protocol whose complexity is log n squared over s plus a negligible term. So they reduced the problem of finding a protocol to the problem of constructing such a set, which I'm not sure would have been very useful if structures like that weren't studied for almost a century. Structures like that and related structures were studied for almost a century in a parallel universe in additive combinatorics. So they were able to reduce this to known results. So this is the first ingredient, using this lemma to reduce the problem of finding a protocol to only showing that it exists by showing that there is such a set without a star that is quite large. The proof of this lemma uses elementary number on the forward communication complexity argument. You can find it in the book of Koshilevitz and Nissan, or go to their paper, Chandra first and Lipton. Of course, they were the first to define the number of the forward model, so they needed and started to develop these elementary arguments. Now, after the reduction, they need to show that such a set exists, and they prove that there is a set S without a star of this size, which gives the complexity of the protocol, this 2 squared 2 log n plus a negligible term. To prove it, they use the reduction to a construction of Berendt of a large subset of integers without 3-term arithmetic progression. I show that if Berendt constructed a large subset of integers without a 3-term arithmetic progression, and they use the simple reduction to show that this implies a similarly large set of triples without a star. The second protocol from 2017 is an explicit protocol. We found it by examining the proof of Chandra, First, and Lipton, and also going into the Behrens constructions and the details and trying to understand what kind of information is really needed to be revealed in order to determine whether x plus y plus z is equal to n. And looking backwards, we understand that there are two main ideas. The first is to embed the problem in the d-dimensional integer grid, instead of considering whether three integers, x plus y plus z, are equal to n. You want to reduce it to the problem of determining whether three vectors, alpha plus beta plus gamma, is equal to some t in the d-dimensional integer grid. Why? Because there is an efficient protocol for the I-dimensional problem. A very nice, very surprising, a nice efficient protocol when the dimension is high, which comes from studying Behrens construction. So for the first step, you want to embed the problem in the d-dimensional integer grid. Instead of integers, you want to consider vectors, summing vectors. A natural way to map integer to vectors is to consider the base q representation of the integers for some q. Then you get the vector of integers. So instead of x, you take the base q representation of x. We'll determine q later. Q and d, we will worry about them later. But we'll make the reduction and the protocol completely general. It will work for any q and any d. And later on, we'll choose them to optimize the complexity. So we take xq and y is mapped to is representation in base q and z as well. And now instead of determining whether x plus y plus z is equal to n, you want to determine whether xq plus yq plus zq is equal to nq. The base q representations. The difficulty is that integer addition has carry, so it's not the usual addition in of vectors, which would have been much simpler. You need to add some correction term that is determined by the carry vector of adding x, y, and z. After you add the correction vector, it's true that x plus y plus z is equal to n if and only if xq plus yq plus zq is equal to nq plus this correction term. So for the embedding to work, you need to compute this correction vector. And since this correction vector is determined only solely by the carry vector of adding x, y, and z, and this carry vector is a 0, 1 vector of length d, then d bits of communication are enough. Maybe less, but are needed. But surely you can do this with d bits of communication. So after d bits of communication, we're in these settings. We need to determine whether three vectors are equal to another vector, where xq is known by two of the players, yq and zq, and this is known by all players, similar to the settings of the previous settings with the integers. So now all we need is an efficient protocol for this I-dimensional problem. Let's make it general. Let's let alpha be xq, beta yq, gamma zq, and t equals nq plus the correction vector, and solve this general problem. You have alpha, beta, gamma, and t in q to the d, the integer grid. Note that for us we need n to be equal to q to the d, or at least larger than it, or smaller than it, something like that. And we want to solve the problem whether alpha plus beta plus gamma is equal to t. There is a protocol for that, a really efficient protocol for that, efficient when d is large. Each player computes privately. No communication is used yet. They compute these vectors. The first player computes alpha plus 2 beta plus 3 times t minus alpha minus beta. They all, in a way, they all would like to compute alpha plus 2 beta plus 3 gamma, but they only know 2 of the inputs, so they fill in the missing piece, but by what they expect it to be. So if alpha plus beta plus gamma is equal to t, then gamma is expected to be t minus alpha minus beta, so that's what the first player fills in, and he computes this vector. The second player doesn't know beta. The second player doesn't know beta, so he fills in for beta, t minus alpha minus gamma, and similarly the last player. So these are the vectors they compute. They all try to compute alpha plus 2 beta plus 3 gamma, but they are missing one of the pieces, and they fill in the missing piece by what they expect it to be, assuming alpha plus beta plus gamma is equal to t. Okay, so they've computed these vectors privately. And what they do now is they want to check whether the length of these vectors are all equal. So the first player writes the length of his vector squared, so it will be an integer on the board for the other two players to see. And then using one bit of verification, the other two players verify that the length of their vector is equal to L. So then they know if the length of all these three vectors are equal or not. Now if alpha plus beta plus gamma is equal to t, if the value of the function is true, it's 1, then obviously the length would be equal, because these three vectors will be the same. They will all be alpha plus 2 beta plus 3 gamma. And the surprising and nice thing about this algorithm is that the opposite is also true. If they're equal, then alpha plus beta plus gamma is equal to t. So the protocol is the first player writes the length of his vector squared, the other two players verify that the length is equal to the length of their vector, and the output of the protocol is 1 even only if they're equal. The complexity, it requires log dq squared bits for the first player to write the length of his vector squared, because that's how many different kind of lengths there could be here in q to the d, plus 2 for the verification bits. And why is it correct? We already said one side is obvious. If alpha plus beta plus gamma is equal to t, then the vectors are equal, then the lengths are equal, and then obviously the output would be 1 as should be. And the nice thing is that if the output is 1, then it must be that alpha plus beta plus gamma is equal to t. Why? Rewrite these vectors we had before, these three vectors. Write them as alpha plus 2 beta plus 3 gamma and plus a correction. The first vector is alpha plus 2 beta plus 3 gamma plus 3 times t minus alpha minus beta minus gamma. And the second is this plus 2 times t minus alpha minus beta minus gamma. And the last is again this alpha plus 2 beta plus 3 gamma, this vector they were trying to compute, plus 1 time t minus alpha minus beta minus gamma. So these three vectors are three vectors on a line. And if alpha plus beta plus gamma is not equal to t, then this these are three different vectors on a line, and their lengths cannot be equal, and thus the output of the protocol must be 0. So this Qt protocol is correct. This protocol is correct for any DNQ. You get this complexity for any DNQ. When you optimize on the choice of DNQ, you take D roughly this, square root of 2 log n, and Q to make Q to the D equal to n, you get this complexity for the protocol. Same complexity as Chandra, First, and Lipton. There is no improvement yet, but having an explicit protocol does shed some new light on the problem and suggest new direction of research and possible improvement. One such direction that seemed natural to us after we saw the explicit protocol is improving on the first phase of embedding and sharing the carry vector. We asked ourselves, do we really need D bits of communication for this phase to communicate the carry vector? And then, as turns out, indeed you don't need D bits. You can use less, as we see in this paper, and we believe that many more bits can be saved on this phase. After thinking about it a little more, or maybe a lot more, and with one or two new ideas, we were able to save some of the carry bits, and this way reduce the complexity of the protocol by a constant. It's based on more or less the same ideas. First, we reduce to a slightly different problem than x plus y plus z equal n to exactly n. But after that step, it's again embed the problem in the d-dimensional integer grid, more or less the same way we did before. And again, find an efficient protocol for the i-dimensional problem, but it's a different protocol. It's not the same protocol. They're based on the same ideas. The fact that in Euclidean geometry you can determine stuff merely by considering the length of vectors. So 3 vectors on a line are equal if their length is equal. And here we use a different property. 3 vectors in space, in Euclidean space, x, y, and z, then z is the midpoint between x and y, if and only if the distance between x and z is equal to the distance between z and y, which is equal to half the distance between x and y. A different statement, but again, the same spirit that you can determine positions or properties of vectors in space only by considering their length, which is awesome, I think. So it's a different protocol in i-dimensional. So the first step, the reduction, we go from x plus y plus z equal n to x plus y equal n minus z, obviously simple, and then 2x plus 2y equals 2n minus z. And then you can easily see that it's equivalent, the problem is equivalent to the problem of asking whether x plus y plus z equals n is the same as asking, given 3 integers, x, y, and z, asking whether they're really an arithmetic progression, really whether z is exactly the midpoint between x and y. So whether x plus y equals 2z. That's the problem we consider. So now we get 3 numbers, x, y, and z. and we want to decide whether x plus y is equal to 2z, whether there are an arithmetic progression. And again, the first step is to embed the problem in the d-dimensional integer grid. And the technique is similar. You consider the representation of the numbers in base q, and you make the numbers into vectors this way. And again, you need some correction vector, this vector here, which is determined solely by the carry of adding x and y. Note now that it's only the carry of adding x and y, and the z player, the one who sees x and y, he knows this vector. So after this stage, which requires to determine the carry vector, previously took d bits, afterwards you get an equivalent problem in the d-dimensional integer grid. This, you have xq plus, we take yq and the correction vector together, is it equal to 2 times zq. And the last step is to solve this problem. You have 3 vectors in the integer grid, and you want to determine whether there are an arithmetic progression, this problem here. And again, there is a really efficient protocol because this equation, vector equation, can be determined solely by the length of the vectors, this Euclidean property, which is nice. So the first player writes the distance between xq and this vector, distance squared, so it will be an integer. And then the other 2 players just verify, check that the distance between x and z is 2 times the distance between x and z is equal to this distance, so 4 times the distance squared, and similarly the distance between zq minus yq and plus the correction vector. And this protocol is correct because, as we said, the vector z is exactly the midpoint between 2 other vectors x and y, if and only if the distance between x and y is twice the distance between x and z and y. Great. So now we have this new protocol. It's different than the previous protocol we've seen. Similar in spirit, but different. But what did we gain here? Why can we save bits here? Why don't we need to transmit all the carry? The point is here that this correction vector, which depends only on the carry vector of adding x and y, is known to the z player. So when the z player computes L in the first stage, it doesn't need any help. He knows xq, he knows yq, and he knows the correction vector. When the first player, the y player, computing this, the distance between xq and zq, verifies that this distance times 4 is equal to L, he also doesn't need to know the correction vector, so he doesn't need to know the carry vector, because it's simply not a part of his computation. And the only player that needs this information is the x player. The z player knows it, and he needs to share it with the x player. And the difference now that he doesn't need to share it with both players, only with the x player, and then they can save communication using the fact that they share information. They both know y. This is where you save some of the carry bits. So why does that allow us to save communication bits? Consider a carry vector of random integers x and y. The carry when adding them in base q. For random x and y, you typically expect that there would be 50% places where there would be a carry. So 50% ones, 50% zeros. That gives entropy of 1/2, which is 1. So you need more or less d bits of communication. But we have shared information, both the z player, which knows the carry vector, and the x player that needs to know from z the carry vector. They both know y, and they can condition the communication on y. They can have one protocol, one transcript, when in entries that are smaller than q over 2, and one transcript where in entries where the value is at least q over 2. And now on those entries that are smaller than q over 2, you expect typically 25% of carry, and here you expect 75% of carry. So altogether you get this expression, 1/2 the entropy of 1/4, and plus 1/2 the average between entropy of a quarter and the entropy of 3/4, which is the same, of course. And now this expression is smaller than 1, and you need less than the carry bits. You gain information by conditioning on the entries of y. And now you can refine this partition and look on finer and finer parts of the vector y and improve on this expression. In the limit, this is what you get. The limit of this is that you can use at most log e over 2d carry bits. And that's it. Thank you for listening, and have a pleasant day.